Good morning, everyone. I'm Tao from ACAT. Is that what? Hello? Okay. So today my talk is about the Parallelized JUNO simulation software based on the SNiPER framework. And first, let me introduce the JUNO. So JUNO is an underground neutrino observatory. So the physics goal is to determine the neutrino mass hierarchy and precisely measure the oscillation parameters. And it's located in the southern China, about 53 kilometers away from the Yangjiang and the Taizhou nuclear power plants. And this is our the innermost part is our central detector. It's a acrylic sphere with a diameter of 35 meters, and it contains 20 kiloton liquid scintillators. And the light yield is about 10,000 photons per MeV. And around this detector, there are about 18,000 20-inch PMT and 25,000 3-inch PMTs. And this is our offline software. Our software is developed based on the SNiPER framework. And this is a simulation. So a muon travels through the detector, and the photons are generated. Then we use the PMT to detect these photons and the digitization, the waveform. Then after that, we have the PMT calibration algorithm to get the charge and the time. Then we could do the event reconstruction, so the reconstruct the vertex or the checking. And the SNiPER master is a task-based scheduler. So to process one event, a task will get a SNiPER task first and run that task once. So in that manner, we can get the events run in could be dispatched dynamically. And this is our detector simulation framework. So it integrates the SNiPER and the Gen 4. And as you know, starting from Gen 4.10, we have the multi-threaded Gen 4 applications. So with the evolution of the Gen 4, it makes possible to run the simulation with Intel TBB, MPI, and so on. So as this page shows. So what we did is derived from the Gen 4 run manager, and the event loop is still controlled by our framework. And before the master run simulation, we have the global task to initialize the master run manager. And this is the software. And then we have the measurement of the simulation. Then an interesting thing is that we found that with the increasing of the number of threads, the speed up is not increased. So we have a look at our code, and finally we found that the problem is there are a lot of photons to accessing the refractive index to calculate the speed. So, however, there is a mutex used in the Gen 4, the material table. So that became a big hotspot. So with that optimization, we get a better performance. So this is the test blade server and our software. And then is the summary. So we develop a framework based on the Gen 4.10 and the SNiPER master, and the benefit from the multi-threading support and the thread safe of Gen 4.10. And our future plan is to use MPI to speed up events such as cosmic ray muons. And this is a prototype. So we have an MPI service to distribute the photons to different workers, and then to do the simulation. So thank you.
Thank you. Thank you. Right. So I'm Philip from IceCube, and today I want to speak about limited Monte Carlo. So very commonly encountered in high-energy physics analysis, we need loads and loads of Monte Carlo. But at the same time, Monte Carlo production, it can be very time and resource consuming. And yesterday, we just heard in a plenary talk in the morning that alone for a high luminosity LHC, it's projected that for Monte Carlo production and storage alone, there will be a need of roughly $1 billion. So that's a lot of money. Furthermore, even if we have a lot of Monte Carlo at our hands, it's often very slow to handle large data sets. So we asked the question, can we just live with a little bit less of Monte Carlo? So if you have less Monte Carlo, obviously, you will be suffering from statistical noise in your sets. And to illustrate these effects, we just generated a toy detector model where we know the exact truth parameterization of the PDFs, and that is shown here on the top. It's not very important now to understand what is this distribution meaning in physics, but basically if you just sample from this distribution 10,000 events and put them in a histogram, you end up with this. So you have this large noise that you want to prevent. There are state-of-the-art tools like variable bandwidth kernel density estimates that you can use to get smooth distributions out of this, and this is illustrated here in the middle. You can see that the distributions are now smooth, but they're not perfectly resembling the shape of the original distributions. And then what we have is called the PISA method that is shown here on the right. So the Monte Carlo that goes into creating these distributions is the exact same as over here. And you see already by eye that this resembles much more closely to where we sampled from to start with. Now, to very shortly describe what this PISA method is doing, so instead of applying smoothing to the final events, we actually we use the Monte Carlo events to characterize our detector resolutions and our selection efficiencies, and these are much more well-behaved quantities, and then we apply the smoothing there. Of course, that doesn't give us the final event spectra, but we can obtain that by convoluting, for example, in the neutrino analysis with the atmospheric neutrino flux and oscillation probabilities of neutrinos. So you have like 4 different ingredients, you convolute them together, and you end up with your final distributions. So how does this look like when you want to run an analysis? This is an example that is trying to measure the neutrino mass ordering. And from the true inputs, we know that the result should be 2.7 sigma. And this graph here illustrates what is the actual result that you get using the different methods with variable input sample size. So if you have a very small Monte Carlo set of just 1,000 events and you throw them in the histogram, you're going to get ridiculous answers of something like 57 sigma in this case, where the true answer would be 2.7 sigma. But of course, if you increase the number of events, at some point it will converge to the right answer. Then using KDEs, it can help a lot, so you get much more realistic answers, but you're still overestimating your significance. And then in green here is shown using our method. It's virtually independent of the input sample sizes, and even for ridiculously low sets, you still get a useful answer. So then in the beginning, I also said it's important to be able to run your analysis fast. So all the methods that I've shown before, also the histograms and the KDEs, we implemented in NVIDIA CUDA to run on GPUs. And just to give you one example, when we started out with our codes, it needed 16 hours to run a full analysis on histograms. And after parallelization on GPUs and some other optimizations in the code, we can do the same thing in 2 minutes. So this is, on one hand, it's very important for the analyzers because it basically gives them immediate feedback, and they can just change something and see what is the impact of this. And furthermore, it also allows us to run more intensive jobs, like, for example, a Feldman-Cousins confidence interval construction, which needs thousands and thousands of trials in your analysis. And this is just a plot showing the relative speed-ups of different methods versus sample size. And this is it. Thank you.
Okay. Yes. All right. Time is short, so I have to run a little bit. I want to give you a bit introduction and sell the library that we developed, VecCore. First, what is the problem we're trying to solve? So, what is vectorization? What is CMD? So, computers have grown in complexity. There are many more transistors available, but not really to exploit parallelism by improving the single performance. So these new transistors were used to make the instruction set more complex, and now there are instructions that instead of, so if you imagine these instructions, instead of processing just a little bit of data, you can process many numbers at a time. So with X2 and AVX512, you can multiply, add, subtract 4 or 8 or 16 numbers at a time. So that's what it is. So why it's so important to exploit vectorization. So this is a graph from a presentation from Intel. It's from binary options. It's a financial code. And here you can see the serial performance. And on the top hardware that they have, this is a bit old, but you can see that you can get 8 times speed up by using vectorized code. And this processor has 18 cores, so you get more or less 18 speed up. And if you multiply the two, that's when you, so when you do both together, then 8 times 18 is 144, plus hyperthreading gets you a little bit more. You can get 180 speed up, which is way above each of them individually what they can do. And Xavi will talk about some similar speed up. There are many ways of exploiting vectorization. So one is you just write code and hope that your compiler just auto-vectorizes it because it knows that this is just a loop and it can process multiple things at a time. You can also give hints to the compiler with OpenMP pragmas or compiler pragmas. Say there's no ignore vector dependencies or force SIMD. You can also use some libraries like VC or UMSIMD. So then you have to declare a new kind of type, but then multiplication, you don't have to do this loop by hand. You can do some express the code in a simpler way. You can also use compiler intrinsics, which is cumbersome and really not portable, and let me not even go into assembly. So VecCore, so why we create the new library? Because auto-vectorization is not always reliable across compilers. Compiler intrinsics, they are limited to CNAME mainly, so it's not an ideal interface. And if you write, even it's not portable within sub-architectures of Intel architecture. So it's really cumbersome. And libraries sometimes don't work across architectures. So some VC is faster on AVX2, UMSIMD is faster on KNL. So we need portable solutions also from ARM when neither of these libraries are available. So we have a simple interface shown here. These are the kind of operations that the API can do: gather, scatter, do masking operations. So in the poster, I wanted to just show a very familiar, simple example, calculation the Mandelbrot set. I showed the simple scalar code where you have a loop of this function, and when it diverges, you calculate how many iterations. So this is the vectorized code with just a few simple changes highlighted here. You can get these big speed ups, 7.74 out of 8x. And on KNL, because of this, the type of the loop that you have, the larger vector is actually not optimal. And here I have similar results for geometry algorithms. And one thing that I want to emphasize is here, VC and UMSIMD work just as well on AVX2, but UMSIMD gains quite a bit compared to VC. But if you look in this picture for AVX2, where I have algorithms for the box, and UMSIMD is in blue and VC is in green, you can see that the backends really can make a big difference. And similar for physics models, VC can bring a lot compared to UMSIMD, so it's not always a simple choice. Usually on KNL, UMSIMD is better, but VC can be also very good on AVX2. So in summary, parallelism is not easy to exploit. different architectures make portability a big challenge, but VecCore lets users express vector code in a portable way with a simple interface, and multiple backends allow the user to choose without changing their code, just change the configuration option at compile time. And if we add new backends in the future without changing your code, you can maybe get vectorization on other architectures for free. And that's it. Thank you.
I guess the sound goes from there.
Well, this is for video. Talk from that side.
Yeah. Okay, to the hub. Okay. I'm here to talk about how we parallelize and vectorize the fitting interfaces in root map in this case. So this was my poster, and this is how we did it. Basically, we chunk the data, we pass it to a scheduler. Each chunk, it's one task, and the tasks are distributed between the threads. Inside each thread, we take advantage of vectorization, and we evaluate the fitting function over 4 points at a time. It's basic. So for this, we used, for the task level parallelism, we use root T-thread executor, which is a map-reduced, task-based multi-threaded map-reduce that's inside root. It's really easy to use. I encourage everyone to use it, and then come back to me with results. And then VecCore, which is what here just presented right now, the SIMD library. The code is mostly backwards compatible. As you can see, there's not a lot of difference. And the only two differences that are there is that you have to specify that the types you're passing will be vectorized types. In this case are doubles. And then you want to specify that the fit is multi-threaded. This will not be necessary once we integrate this inside the implicit MT. Okay, it will do it by default. So case example is this famous fit, Gaussian plus an exponential. And this is the kind of speed up we can get on your PC, your laptop, your desktop, whatever. And as you can see, it's not only limited to one of the distributions of the fitting functions. The Poisson likelihood and the mean likelihood perform really well. The chi-square used to perform really well, but you will have to trust me for that. Right now we are in a bump, but I don't know. There's a lot of modifications in the code, and maybe we can get back to it soon. The multi-thread speed up, it's pretty good too. Of course, it cannot be perfect, but you get a really nice speed up. And then it performs mostly equally between compilers. You can see that ICC there. I don't know why it performs a little bit slower, but then there's a nice curiosity that's that ICC without the vectorization was basically, if we don't turn out auto-vectorization, it vectorizes the same at the same level as the other ones with explicit vectorization. And that's it. I kept it simple.